look for okay. Yeah, so this is our equation. HA, the acid, goes to H plus or H3O plus, that's what we're going to be looking for, plus A minus, the thing without the hydrogen. So we're looking for something like this. We have our hydrogen attached to the conjugate base. Then the hydrogen pops off and attaches to water. And then we have our conjugate base. So then we need to do this equation. Our equation is kind of like our equilibrium expression from chapter 6. We have the products over the reactants. So the concentration of H3O plus times the concentration of A minus all over the conjugate base, the conjugate acid, HA. And then we just rank our acids in strength. Okay, so the first one, where's the mouse? So we count the hydronium, 1, 2, 2 hydroniums. We count the conjugate base, 1, 2. Okay, that should always be the same number. Good thing they're the same number. And then we count the original acid, HA. So there's only 1. So this Ka for acid would be 4. So then we go to the next one, K2. Look for hydronium. 1, 2, 3 hydroniums. That means we better have 3 of the conjugate base. 1, 2, 3. And then we're going to divide by the conjugate acid, the acid how it started, with the hydrogen, without giving away the hydrogen. 1, 2, 3, 4. So that would be 9 over 4. Okay, K3, the third acid. We have 1, 2, 3, 4, 5 hydroniums, 5 conjugate bases. We have 0 of the conjugate acid, the original acid. So this automatically tells me that it's a strong acid. This is going to be the strongest. So if there's no original acid, that means all of them broke apart. That's the strongest acid. That's a strong acid. Okay, next one, we have hydronium. 1, 2, 3 hydroniums. We have 1, 2, 3 conjugate bases. And we have 1, 2 conjugate acids, 2 original acids. So this is 3 times 3 is 9, divided by 2, 9 halves. Okay, so then we rank them. So this is going to be the strongest because it is a strong acid. So 1, and then we look for numbers. So this is 4. What's 9 divided by 2? Is that 4.5? And then what's 9 divided by 4? The 2 point something? Okay, thanks. 2.4. So this one's gonna be the next one. This one, and then this one. So we're ranking them in by the value. So strong acid is gonna be the strongest. Then this one is 4.5, so it's the next strongest. Then this one is 4, and then this one is 2 something. Weakest. Okay. Questions on that one? Do you want to do another one?
Yes.
Do one. Another one.
No.
Okay. Questions on this one? Do you see the process? Just counting, multiplying, comparing. Okay. Again, so we're looking at products over reactants. So our products are hydronium. We've got 1, 2. So 1, 2, 3. 3, and then our original acid or conjugate acid, 1 base, 1, 2, 3. divided by the acid, one of those. So the acid is the one with hydrogen. This one's the acid. This is the conjugate base, and then this is hydronium. Okay, so the next one, we're looking for hydronium. We've got 1, 2, 3. We have our conjugate base, the one without hydrogen, 1, 2, 3. And then we have our original acid with the hydrogen, 1, 2, 3, 4, 5. So this is 9 over 5. K2 or 3. Oops, that's 3. There we go. Solution 3. So look for hydronium, 1 times the number of conjugate base without the hydrogen, 1. That's good to match. Then we count the original acid with hydrogen, 1, 2, 3, 4. So that's 1 over 4. And then the last one is K4. We're looking for hydronium, 1, 2. We're looking for the conjugate base without hydrogen, 1, 2. Now we're looking for the original acid, the conjugate acid with hydrogen. None of those, 0. So if all of them have dissociated, that's going to be a strong acid. Strong acid. So that's going to give us a number 1, strongest acid. Okay, then we have to figure out the other ones. This one is 9. That's a big number. 9 divided by 5 is going to be the next number. And then 1 divided by 4 is going to be the smallest acid, the weakest. Smallest number, weakest acid. So this one's the weakest. That was the strongest. This one is the next strongest, and this is the third strongest. Okay. Questions on that one? You think you could do that? Okay, do you want to do another one? Okay, let's do another one. All right. So does this part, like what we're looking for, make sense? Okay. All right, so this first one, K1, we're going to look at our products, which are hydronium. There's a hydronium. Times by the conjugate base, so no hydrogen. There's one of those. And then we're going to divide by the original acid with the hydrogen. 1, 2. 2 of those. So this would be a value of 1/2. Then we're going to move to the next solution. This solution has 2 hydroniums and 2 conjugate bases without hydrogen. And then we're going to divide by the original acid. We have 1, 2, 3, 4, 5, 6 of those. So our value will be 4 over 6. Okay. Third solution. We're looking for hydronium. 1, 2, 3, 4. Then we're looking for the conjugate base without hydrogen. 1, 2, 3, 4. And then we're going to divide by the original acid. Oh, there's 1 right here, 1. So this would be 16 over 1. That's a big number. And then the last solution, look for hydronium. We have 1 hydronium. And we have 1 conjugate base. And then we're going to look for the original acid with hydrogen. So 1, 2, 3, 4, 5. So that will be 1 over 5. Okay, so this one's the biggest number. So biggest number gives us the strongest acid. And then we have to figure out which one is the next biggest. Let's see, I'm just going to grab a calculator, I think. That'll be the easiest for me. So I know this is 0.5. I don't know. This is a third point. No, 2/3. 4 divided by 6 is 0.67. And 1 divided by 5 is 0.2. So let's see. So this is going to be the next biggest number. Then this number. And then this number is the smallest. So it's going to be the weakest. Yes? Yes, strongest acid. Yep. Yes, and you will only ever get one of those. You don't have to compare strong acids. Yep. Yes, that automatically, if there's no original acid, none with hydrogen, that's automatically number 1. Yep. You're welcome. Okay, this one was the biggest, K3. And then this one. So this one's the second biggest. And then this one. And then this was the weakest. Just by ranking them. Okay. Are we you can do that now on the test? Okay. All right. What was the next one? I know the pH one was up there. Let's do that one. Calculating the pH of a strong acid. I think this is the next most missed question. So this one, we have to know the acid. So you either have to put the acids on your note card or you have to memorize them. So I don't know if I have that sheet anywhere, but you need to know that. Okay, so this one is 170 milligrams of pure iodic acid. So I'm going to first convert that to grams. And then I know the HI is hydroiodic acid. And then, let's see, what else we need? Enough volume to make up 90 milliliters. So we need to convert that to liters. 0.090 liters. So the first thing that I need to do is I need to find the moles. Find moles of acid. So I'm going to take the mass. I'm going to divide by the molar mass. And that's going to give me moles of hydrogen. Okay. That's why you need to know the formula of this, because you need the molar mass. So figure that out. Either put that on your note card. Oh, here they are. Either put the strong acids that you have to memorize on your note card or memorize them. So I'm going to take my mass, divide by the molar mass, which is hydrogen plus iodine, and that's going to give me moles. Just need a little bit further. There's the calculator. 0.17 divided by the molar mass, so I'm looking for H and I. Oh, 1H. Oh, did I do it? Oh, I clicked on the wrong thing. Okay. 1H plus 1I. Okay, so mass divided by molar mass. So this is the number of moles. And then the second thing is I'm going to take the moles of H plus. I'm going to divide by the volume. Okay, and this is going to give me the concentration of H plus. So take this, divide by the number of liters in liters. This is 0.09 liters. So this is my concentration of H plus, 0.01476. And then the third thing I'm going to do is I'm going to use this equation. The pH is negative log of the concentration of hydrogen. So I'm going to do negative log of the number that I just found. And that will be my answer. So I'm going to do log, and it's the negative log. And then remember, you have to keep, when I take the log, I need to keep the same number of decimal places as my least sig figs. So this value has 3 sig figs. This value has 2 sig figs. So I'm going to go with my least sig figs. So my answer needs 2 decimal places. So I'm going to do 1.83. That's 2 significant decimal places. That's a new rule for sig figs with the log. Okay, keep as many decimal places as your least sig fig that you use. This is not going to tell you that on the test, so you need to remember that new rule for sig figs. Okay, on this question, pH should not be negative in our class. So if you get a negative number, check it. If your pH is above 7, that's also wrong because these are acids. Acidic pHs are below 7. Your pH should probably be between 1 and 3 because these are strong acids. So if you get something that's 4, I would double check. Make sure you did it right. Okay. So those are some ways to check.
So
yes.
I was doing one and it's like I needed 4 sig figs, even though my starting number is only 3.
So look at your decimals. You should have 3 decimals.
You don't have sig figs. Which ones have sig figs?
Oh. Okay.
That's a new rule with logs. Yes. Okay. Other questions? Okay. Do you want to do another one of these?
Yes.
Okay, let's do another one. Okay, I'm gonna erase this. So take the mass. Oh, they're giving us nice acids. So first, take the mass, convert it to grams. So this is 0.202 grams of hydrobromic acid. That's HBr. Okay, and our what is that called? Volume is 0.320 liters. I'm gonna convert that right off. Okay, so the first thing I'm gonna do is I'm gonna take my mass, 0.202 grams, and then to divide by the molar mass. And I know the molar mass because I know the formula, H plus Br. Oh. 0.202. Oops, I didn't get a decimal in there. Divide by the molar mass, which was hydrogen. Oops, do we get hydrogen? I don't think I clicked on it. Hydrogen plus bromine, hydrobromic acid. This is the number of moles of hydrogen. Then I'm going to divide by the volume. So moles of H plus divided by the liters. That's going to be the concentration of hydrogen. And then the third thing is I'm going to use the pH equation. pH is negative log of this number. Okay, so now I have the concentration of hydrogen. Now I'm going to do the log. I'm going to do the negative log of this. Oops, that's a pop. I push equal. How do I do undo? Undo, negative. There we go. So it'll switch the sign. Okay, and then I need to check sig figs. This has 3. I use this number. I use this one, 3. So my answer needs 3 decimal places. 1, 2, and I'm going to round that to an 8. 2.108. Okay, questions on this one? You think you could do this? All right, let me check.
The next question. And last year, on base, identify.
Okay, let's do the next one. Identifying the volume of base. This is the titration question. Identifying the volume of base. Oh, determining. Determining the volume of base needed to titrate given a mass of acid. Okay, so for this one, they give us a mass of acid. This acid, they're going to give us the formula. We don't have to memorize it. This one is phosphoric acid, H3PO4. And then we are going to also use this value. This is the concentration of base, 0.1100. And we talked about how what we're looking for is when the moles of acid are equal to the moles of base. And that's how we can figure out when these are equal to each other. That's how we can do some other calculations. So we can find the moles of acid from this volume. And then what we can do is we can switch this. So moles of H plus is equal to the concentration of hydroxide times the volume of hydroxide. Because remember, concentration times volume gives us moles. So when we added the same amount of acid as base, then we can relate these. That's why we can do this. So I think that will make more sense once we do the titration math. Okay, so what we're going to do is we're going to find the moles of hydrogen, and then we're going to divide the moles of hydrogen by the concentration of hydroxide. And that will give us the volume of hydroxide that we used. Okay, so we have to figure out how many hydrogen ions this is going to make. So we're going to take our 0.167 grams and convert it to moles by dividing by the molar mass. And that's going to give us the moles of phosphoric acid. That's a little zero. Okay, so let's do that on our calculator. So 0.167 divided by the molar mass. So we need to know how many hydrogens. Well, we have 3 hydrogens. 3 hydrogens plus 1 phosphorus plus 4 times the oxygen. Okay, this is the number of moles of the acid, but this is telling me it's triprotic. That means for every 1 acid molecule, I get 3 protons off. That's also telling me, do you remember we talked about, we have this equation, H plus OH gives you water. So now it's neutral. So that's going to tell me I need 3 times the base to cancel out all of these H pluses. So I need to multiply this by 3 because it's triprotic. So I'm going to take that number, multiply it by 3. Okay, so this is how many hydrogen ions, how many moles of hydrogen. So then, once I have moles of hydrogen, I'm going to divide it by the concentration of base, which was 0.1100. And this is my volume in liters. So the last step, I guess, I need to go from liters back to milliliters. So I'm going to multiply by 1,000. One, two, three. The 2 values, this one has 3 sig figs, this has 4. So my answer can have 3 sig figs. So this will be 46.5 milliliters of base. 46.5. Okay. Yes, Chloe. Yes, will you take the hall pass? Thank you. Do you want to do another titration problem? Okay, yes, all right. Okay, I'm gonna erase this. Okay, we have a new acid, hypochlorous acid. The mass that they give us is 0.112 grams of hypochlorous acid. Okay, we've got our formula. This is also a monoprotic acid. We only have one hydrogen. So if we calculate the mass, we'll get one hydrogen for one acid, 1-to-1. And we have base. Our concentration of our base is 0.1200 molar sodium hydroxide. So the first thing we're going to do is we're going to find how many moles of acid we have. So this one we're going to do 0.112 grams. We're going to divide by the molar mass of the acid. That'll give us the moles of HClO. So let's do that. I don't know, this looks like a weird number. I'm just going to fix it. 1. 0.112 divided by the molar mass. So we've got hydrogen here. Hydrogen plus a chlorine plus an oxygen. Does that work? Yes. So mass divided by molar mass gives me the moles. And then for this acid, this will give me one hydrogen for one acid. So I just would multiply by 1, but that will give me the same number. So the next thing I'm going to do is I'm going to use this equation. Moles of acid, or H+, moles of H+ divided by the concentration of OH will give me the volume of base that we need to add. But remember, this is in liters. So, ooh, that looks funny. In liters. So what we need to do is we need to take our volume in liters and multiply by 1,000 so that it's in milliliters. Okay, where are we? This was our moles of H. Okay, we're going to divide by the concentration of base, and that'll give us the volume of the base. So we've got 17.8 milliliters. Okay, the other thing I'm going to check here is make sure, so this one has 3 sig figs, this has 4, so I'm going to go with 3 sig figs. 1, 2, 3. Okay. All right, questions on this one? Did that one, we're catching on, we're doing okay? Okay. The last one that we'll go over together, unless there's other ones, is the identifying strong or weak acids from a sketch. Okay, so when I'm looking for a strong acid, I'm looking for the acid to completely dissociate, and then all the hydrogens have to join hydronium, or water to form hydronium. So this one doesn't have any acids. This one is showing something that hasn't given away any protons, so that's not helpful. This one would be the strong acid because we have the counter ion, the conjugate base. All of them are without hydrogen, and then we have the hydrogens attached to the hydronium. That's a strong acid. When all of them completely dissociate, all the acids. So that's the best one. This one is not. This one, the hydrogens are floating around. We cannot have the hydrogen just floating around. This one doesn't have any acid. It just has hydronium. This one would be a weak acid because only some of the hydrogens have dissociated and nothing happened here. So our best one was, I think, 3. Strong acid. Okay, weak acid, we're looking for the acid to not completely dissociate. Some of them have to dissociate, but not all of them. And then any hydrogens that come off of the acid should go to hydronium. This would be a strong acid. All the hydrogens are popped off of the acid. This one would sort of be weak acid, but the hydrogens have to be attached to hydronium. So let's see. So this is looking better. We have some original acids, some conjugate bases, and then any hydrogens that popped off went to the hydronium. So 7 is looking good. Nothing came off, so that's not an acid. Okay, let's do another one. So we just did weak acid. Let's go through and find it really quick. Oops, I missed it. Oh, that was the first one. Great. So this one, only some of them are dissociated, and all the hydrogens joined water to form hydronium. I think the weak base is the hardest for me. What I'm looking for is some of the bases accept a hydrogen from water. So that's not true. That's not true. So this is what a weak base would look like. We have some kind of base. Some of them are accepting a hydrogen from the water, but not all of them. That is what a weak base should look like. Okay, we have not seen strong base, so let's find strong base. Okay, strong base, we're just looking for hydroxide and then the counter ion, and all of them have completely dissociated. So this looks good. We have our, we have hydroxide, so check for hydroxide, and then we have our counter ion that's balancing. So it's like sodium hydroxide, and all of them split apart. Weak base, we're looking again for only some of the base is accepting a hydrogen from water to make hydroxide. So this would be our weak base. This one has accepted a hydrogen from some water. There's a hydroxide. This one has also, there's a hydroxide, but not all of them have accepted a hydrogen. That's weak base. Okay, questions on that one? Are there any other ones that you want to go over? Those are the top, I think, 5 most missed questions.
Can you do one more for the predicting the products of the neutralization reaction?
Yes, predicting the products of a neutralization reaction. Yes. Okay, so this one, whenever we add 2 strong acids together, we will always get water and then some kind of ionic compound. So this one is HClO4 and NaOH. I see 1 hydrogen and 1 OH, so that will form 1 water. So this one we won't have to balance, so that's nice. So then whatever's left is the ionic compound or the salt. So I have sodium and I have chlorate, perchlorate. So I'm going to write the sodium first. It comes first in the formula. It's a metal. It has to go first. And then perchlorate is going to come second. So I will have water and then sodium perchlorate. H2O. Let's find one that we have to balance. Okay, so I look at this one and I see there's 2 hydroxides. So let's see, we've got HClO3 and we have barium hydroxide. We've got 2 of those. And that's going to form something. So the hydrogen is going to react with hydroxide, but we need 2 hydrogens to react with 2 hydroxides. So the only way to get another hydrogen is to give us a whole nother molecule of this. So I'm going to form 2 waters here. Okay, does that make sense? And then I need to figure out what else I formed. Well, I have barium. Barium's going to go first. And then I have chlorate, ClO3. Barium is a 2+ charge. Chlorate is a 1- charge. So I'm going to need 2 chlorates to balance the barium. So this one, I needed 2 of the acids to balance the 2 hydroxides, and then I needed the 2 chlorates to balance the charge on the barium. So this would be 2 water, oops, barium, oops, 2. Okay. Oh, and I need to change this to a 2. I needed 2 acids to balance the 2 hydroxides. Okay. Does that answer your question? Okay. Other ones that you want to go over? Yes. Okay. So this one, when we see it's weak, we're going to get 4 species. We're going to have the original acid just as it is. We're going to have the hydrogen ion, and then we're going to have the conjugate base, and then we'll also have water. If it's a strong acid, the acid will completely break into hydrogen ions and the conjugate base. It's not going to have any of the original acid with hydrogen. So this one's weak. So we're going to get the original acid. Oops. So because it's weak, some of that will stay. It's not strong enough for all of them to break apart. And then we're also going to get H+. So some of it will break apart into H+, and then the conjugate base, ClO2-. And then we'll also have water. Oops, is that, oops. I wasn't sure if it was touching. Okay, so all of these should have water. All of them should have hydrogen ion. If it's strong, we'll only have 3 species. We'll have water, hydrogen ion, and the conjugate base. So this conjugate base is NO3. Okay, this one's weak, so we're gonna have water. Oops, I thought I copied water. Hydrogen ions, we'll have the conjugate base, so we're gonna go down, down 1 hydrogen and down a charge, HS-. That's a conjugate base. And we'll also have some of the original acid. Because it's weak, not all of it will break apart. This one's also weak. We're going to get water and the H+. We're just going to copy paste that. Then we're also going to get some of the conjugate base, which is down 1 hydrogen, down a charge. And then we are also going to get some of the original acid, H2CO3. Oops. What is it saying? Your answer, the charge on one is, I didn't put a minus charge on the conjugate base. Does that answer your question? Okay. Other ones you want to go over?
We already did, we do one more.
Yes, yes, of course.
Volume of base you did.
Yes. Yes. Determining the volume of the base. Okay. So this one says it's diprodic. So that means for every mole of acid, we're going to get 2 hydrogens. So that means I have to multiply by 2 so that I have the right amount of base. Because I'm going to need 2 base molecules to cancel out one of those. Because that has 2 hydrogens. Okay, so we have our mass. So the mass is 0.426 grams of the acid. So the first thing I'm going to do is divide by the molar mass. And that's going to give me the moles of acid. Then this one we're going to have to multiply by 2 because it says it's diprodic. Because there's 2. Okay, so let's do that up to that point. So moles of acid, 0.426, 0.426 divided by the molar mass. So this one's, we've got 8 hydrogens. Hydrogen times 8 plus we have carbon times 6 of those plus 6 times oxygen. So this is going to be the number of moles of acid, but we need hydrogen ions, so we're going to multiply by 2 because we're going to get 2 hydrogens for 1 mole of acid. Okay, so this is the moles of H+, and then we're going to use this equation. Moles of H+ equals the concentration of hydroxide times the volume of hydroxide. So this only works when we've added the same amount of base and acid. And that's what a titration is. Okay, so then I'm going to divide by the concentration of hydroxide. I'm trying to find the volume. So divide on both sides. Concentration of hydroxide. So the volume of hydroxide, this is giving me in liters, is equal to moles, of hydroxide, or hydrogen divided by the concentration of hydroxide. So we have our moles of hydrogen now. We're going to divide by the concentration. This is the volume in liters. So then I need to convert it to milliliters. And then I need to check sig figs. So this has 3, this has 4. These are the only 2 numbers I used. So I'm going to need 3 sig figs. So this will be 34.6.
So you didn't even use the 200?
No.
Okay.
Yep. Because I can find moles of acid with just this number. I don't need the concentration. Okay. Do you want to do another one of those, or is that you're good? Okay. Yes, another one. Okay, let's do another one. All right, this one is acrylic acid. That's a monoprotic. It won't tell you that it's monoprotic. So if it doesn't say diprotic or triprotic, then there's only 1 hydrogen for the acid. So we're going to take the number of grams of acid, 0.0367 grams. We're going to divide by the molar mass, which we have to figure out, and then that will give us the moles of acid. This one is 1-to-1. We get 1 hydrogen for 1 mole of acid. There we go. So we would be multiplying by 1, but we don't need to do that. We know what will happen. Okay, so 0.0367 times by, divide by the molar mass to get moles. Okay, this one, let's scoot it over a little bit. Acrylic acid has 4 hydrogens. Hydrogen times 4. 1, 2, 3, 4. It has 3 carbons. 1, 2, 3. 3 carbons. It has 2 oxygens. So this is the number of moles of acid, but also the number of moles of this hydrogen ion that can come off when we add a base. Okay, so then the next thing we're going to do is once we have the moles of H+, my marker is dying, then we're going to divide by the concentration of hydroxide, and that will give us the volume of hydroxide in liters. So we're going to take this number, divide it by the concentration of hydroxide. This is the volume in liters. We don't want it in liters, we want it in milliliters. So I'm going to move the decimal. 1, 2, 3. Oh, this one we have extra, so we need 3. And we have a 5. So we're going to round this one to 3.00. Let's check. We got 3 sig figs and 4 sig figs. So we're going to go 3. So 3.00 milliliters. I'm rounding up to 3. That's very close to 2. Oh. Check. Okay. Okay. We've got that little noise means 10 minutes left. Is there any other ones you want to do? Okay, I'm gonna let you work on that. If you come on Wednesday, we'll review again. If you don't, then you should review on your own and be ready for the lab on Tuesday, tests on Thursday, next Thursday.